networks and economics, and I'm going to split.
Yeah, here we go. More time on the economics to begin with. So I'll give you a little bit of economic background, and then that'll set up a learning model. And I'm going to start here. Just with background on homophily. And so one thing that's extremely important in predicting economic outcomes seems to be how split graphs are. So what's the strongest split you can find in terms of a graph? And this is a picture of a high school. Each one of these little dots is a student, and they're color-coded by race in this case. And the line between two students indicates that they're connected in terms of naming each other as people that did at least 3 activities in a given week. So this is from Ad Health. And what you see is that there's a pretty strong split. So this is just drawn with a Spring algorithm. So it pulls together nodes that are connected, pushes them apart if they're not connected. And you can begin to see that even though the school is fairly racially diverse, when you actually look, it's integrated on paper, but when you actually look at the friendship patterns, it's heavily segregated. And so one thing we want to understand is what are the implications of these kinds of splits in graphs that you see. So this is from the Ad Health data. This is from a study with Sergio Curarini and Paulo Pin. You can also see this. This is from another study we did in Karnataka, southern India. This is a village. These are households now. And this is a kerosene and rice sharing network. So this is, people borrow and lend kerosene and rice. In this case, the nodes are now colored by caste. So the red dots are scheduled castes and scheduled tribes, which are relatively disadvantaged caste groups. The blue squares are general merit and otherwise backward castes and relatively advantaged castes. So here again, you see, in this case, there's about a 15 times higher chance that 2 nodes are connected if they're of the same caste designations. And you can run, community detection algorithms on this as well, and you'll see that there's additional splits among the scheduled castes and scheduled tribes.
You know the characteristics of the persons on the boundaries connecting to community?
Yes, actually, we do. So, I can tell you some anecdotal stories about those. They actually tend, so, there's a theory in sociology, Ron Birch's, bridges between communities tend to do very well. In these communities, they actually tend to be marginalized individuals. So often they're widowed households, other kinds of, so when you look at these households, they don't tend to be the higher households in terms of wealth or other characteristics. They tend to be somewhat peculiar households for one reason or another. But there's interesting patterns. Those data are actually available on the web if you want to play with them. So we have 75 different villages, and you can look at the structure of these. But this kind of homophily is something that's quite prevalent. It's there in a lot of different settings, and it has consequences. And one of the consequences I want to talk about is economic inequality and immobility. And I'm going to show you some data about that in a moment. And then we'll talk about how network models can help us, help inform us about these kinds of issues and why we might think that this is related to networks. And I think over time, I've become convinced that in terms of a social scientist perspective, understanding these splits in the graph and understanding these homophily structures is really fundamental to understanding why we have strong divisions, inequality, polarization, other kinds of things in the society. So I think it's a fundamental driver of these things, and I think it's part of the reason for spending today's lecture on this is to try and understand some of the consequences. So one other piece of background, things to keep in the back of your head, what's known as the Gatsby curve. So this is something that was popularized by Alan Kruger in a presentation to Obama in 2012, I want to say. And what this is it looks at 2 different things. So it's looking at immobility on this axis. So immobility is what's the chance that a child looks different than the parent. So immobility is correlation between child's income and parent's income. So in particular, it's a coefficient on a log-log regression. So it's basically a correlation coefficient of how correlated is a child's income with a parent. So really high correlation means that once I see your parent, I know how you're going to end up in your future. So if things are fair, you should see pretty much zero correlation between parent and child income. If things are unfair, the parent's income determines the child's income. And then on the other index here is the Gini index of inequality. And this is an index which basically asks, if you randomly pick two individuals from the society, how much more wealth would the richer person have compared to the poorer person? And if that's zero, then there's pretty much even income distribution across the society. If it's one, then basically the richer person would have 100% of the wealth. And so what you see here is that countries that have higher inequality also have higher immobility. This also works on microcosmic levels. So if you look within the United States, you look at this by zip code, you look at this by county, you'll see a similar pattern. The counties that have the most inequality have the most immobility. Okay, and part of the reason that this is interesting is networks, naturally have these kinds of feedback features where if you're in a sort of a bad position in a network and you aren't getting resources, you're not getting information, you're not getting things, then that can perpetuate itself. And so when you look at network models, they tend to have the feature that they'll give you both of these things at the same time. Okay, so that's just another thing to keep in the back of your mind. Okay. Next piece of information, economic information to keep track of, is the geography of upward mobility in the United States. So this is a map of, just looking at a person, look at a kid in the 25th percentile of the income distribution in terms of their parents' income. So this is a person who's in the poorer quarter of the society, and then ask what's their income going to be when they grow up. Okay, and so this is data from Raj Chetty and a team of researchers from 2018, and this is just a map by the US. And there's a huge amount of variation. So these are just average incomes, and what you'll notice is that there's geographic patterns to some of this. So there's whole parts of the country where kids that grow up in the bottom part of the income distribution are going to stay there, other parts where they tend to rise out of. Yeah, so North Dakota and South Dakota are fascinating places, and you'll see that popping up in a bunch of maps I'm going to show you a little in a couple of minutes. So actually this whole part of the upper middle west is high on pretty much a whole bunch of scales.
What are these red spots in the middle of this?
Those are actually Native American reservations. Both of those are Native American reservations. I don't know Maine that well, so I can't tell you exactly what that spot is. Yes.
How does it take into account actual mobility of people moving from different states? Is it the state of the parent or the state of the child?
So this is actually looking at a child's income, and it could be that the child ended up in a different place. So this is looking at the place where the child grew up, and then eventually just asking what their income ended up being. So it can also be that some of the children here stayed in this area, and some of the children here actually moved to New York or moved to San Francisco Bay Area. So it's not, so there is mobility as part of this. And I can tell you, there's a lot of interesting things about income and mobility that take us way off topic, but it's important in what's going on.
And I'm guessing that this is somehow normalized for the phase of life where the parents were and where the children are now.
Yes, so this is looking at age 35 of people in 2014. So it's looking at one slice of people, and it's you can do this in different scales. This is actually in actual dollar scales, household incomes, but you can also do it in relative, just percentiles in the US and so forth. There's cost of living, other kinds of issues that are going on. There's lots of things to take into consideration that I'm not going to try and get into, but
is it the average income of the parents when these children were 5, or the average children? So
this is take the children whose parents earned $27,000 when they were kids. So take the kid. So take a 35-year-old now in 2014. Look at when they were a child. Ask what their parents' income was. Look at all the kids whose parents' income were $27,000 when they were a kid. and now ask what the current kid's income is. And that's what this number is. So these are all kids who had parents who had the same income when they were kids, and then looking at the kids' income when they're adults. And so you see a huge amount of variation across the US. Okay, so part of the reason for being interested in this is that, again, inequality, mobility, norms, jobs, learning are all impacted by homophily. And I'll talk a little bit about more, about why we care about these kinds of structures in the networks and why that might be related to this. And so this afternoon, what I'm going to do is a little more background on homophily, and then we're going to look at a particular learning model. And part of the reason for looking at that learning model is it's a nice model in terms of capturing how homophily relates to the specific outcomes. But I think it's a metaphor for a lot of other dynamic processes on networks that would have similar features. So it's sort of an example of the kind of features you might be interested in. So next, what I'm going to do is show you a paper, actually data from a couple of papers that we just released. These are with Raj Chetty, Teresa Kukler, Johannes Strobel, and then a large team of people. This is on Facebook data. We released these a few weeks ago now. And it has a pretty rich set of data about exactly what's going on in the graphs and so forth, so we can understand the homophily and we can understand the consequences. And I want to show you some of those. Okay, so what we used in these studies were Facebook users. We did a cut in May, so a couple of months ago was the last draw of data we did. Ages, we're going to look at people who are 25 to 44-year-olds. That's because they have the really high usage, and we're able to trace back to what their parents' income were when they were kids and things like that. So we can do things from that slice of life. These are going to be active users with at least 100 friends. So it's 72 million people, 21 billion friendships. It's 84% of the coverage of people in the United States. And then we have a lot of information about them. We have the friendships, a lot of demographics, geography, memberships in different groups, where they went to high school, college, recreation groups, churches, et cetera. And then we're going to marry that with census data and a bunch of other things. And in terms of,
Sorry, can you tell us something about which 70 million users these are? Like how do you sample that?
Yeah. So basically what we were using is, so it's anybody on Facebook who is at least 30-day active and has at least 100 friends. I have.
Did you get that data?
How did we get that data? So Mike Bailey, co-author here, was a student at Stanford. So basically, Raj and I started talking about how do networks impact mobility and economic outcomes. Mike Bailey was someone we knew from him being a student at Stanford. Teresa and Johannes were also students at Stanford. They've been working with Facebook data, so we teamed up, and then the list of large numbers of incredibly useful and very hardworking co-authors were people who were basically, as you'll see, doing different measures on the data. In terms of the coverage of Facebook data, so we're looking at pretty much anybody who has a Facebook account who is 25 to 44 years old. And then, yeah, so we look, how do we know what age they are?
Everybody on there who fits those criteria.
Yeah, exactly. So it's a full sample. It's not like we're pulling random. Yeah. So it's pretty much any. So we're looking at 84% of the U.S. population between the ages of 25 and 44.
So you're saying that even though everybody says Facebook is dying out, actually 84% of the U.S. population has more than 100 friends on Facebook and is active.
Yeah, of the 25 to 44-year-olds. So it's actually, the demographics are quite interesting. So among people below 25, Facebook is dying out. So and we actually use Instagram data to look at younger people for part of the study. So we looked at younger people and made sure that the things reproduce with younger group. They're on Instagram. So it's very different by different ages, usage patterns. The older people are also there, but they wouldn't be useful for the kinds of questions we're going to ask. Yeah, but there's a really marked drop off. It's like a cliff in terms of the age dynamics on Facebook. And so that was 25 was the reason we used it. Okay, so one key thing we're going to do then is, so one thing we do is we use a series of machine learning techniques to impute people's income. So we have information on where people live and a whole series of things about them, what kind of phone they use, what computers they use, whether they went to college, a bunch of stuff. We use that, and we also have census income data, so we can pinpoint the income of the area they grow up in, and we basically train a model to predict income. And so then from those income designations, what we're going to do is look at economic homophily, right? So before I showed you a picture of like homophily across castes or homophily across different ethnicities within a high school, what we're going to do is take people who are in the bottom half of the income distribution and ask how connected are they to the people in the top half of the income distribution. Okay, so we're just going to cut it in half and then say, look at the bottom half of the distribution. So economic connectedness is number of friends with above median income, basically, over the total number of friends, then divided by a half. So this should be a half, right? This ratio should be a half if you just had a normal representative group of friends. If this is bigger than a half, it means you're more connected to the rich. If it's smaller than a half, you're less connected. Okay. So this is, first of all, just the mean. If you look at somebody's rank in the income distribution, this is the rank of their average rank of their friends. So there's a lot of homophily. And one thing that we do is you can look at top 10 friends as opposed to all the friends. So top 10 is based on your interactions on Facebook, whether you're posting and commenting on each other and so forth. So it doesn't really matter whether you're looking at top 10 friends or others, you see strong homophily. So the fact that this is not a flat curve is indicating that there's different friendship patterns among the poor compared to the rich. Question?
It's maybe because I'm 99 years old on Facebook. We don't ask for the income on Facebook, right?
No, so I can tell you a lot more offline about how we do that. But there's a lot of, so we basically use 22 different variables about a person. Okay, so the census data, so take the census data, for instance. Let's suppose you grew up, you live on 7th Street and 3rd Avenue in New York. Okay, the census. So we join those two things, and then we can take all the demographics that we know about you, plus your geography, predict your income. So we train a model based on that, and then we use it to impute these incomes. And then we also we check whether or not this matches up with census data, and then a whole series of other things that we know.
Question. Do we know anything about the bias of being on Facebook or not based on, for example?
Yes, yeah. We have lots of a long appendix about that. And given the fact that we have 84% of the population, we basically don't have much of a bias. There's differences among the patterns here, but yeah, I should just, I can show you a graph later. I have a graph of the actual geographic coverage, and the geographic coverage is quite, it's like a checkerboard. There's no real pattern to it. So we don't see systematic biases in the Facebook coverage here. We also match this up with the @health data and check that it looks like the @health data in terms of income distributions and so forth. It does seem to match up. So there's a lot of robustness checks. I think the data are pretty good. We won't get causal inference out of here, so we'll be able to look at these and then I'll tell you about what some of the outcomes are, and there'll be some questions here, but I think the quality of the data seems to be pretty good. On some dimensions.
Facebook, I'm 90 years old, but Facebook knows how old I am. So
Yes. Yeah. I mean, we like, for instance, we match people to high schools. Guess what the most popular high school in the United States is on Facebook? Hogwarts. So you need to work a little bit on the data to actually figure out what high school people went to, but it's possible. So there's a lot of stuff that. Yeah, I mean, you can still figure it out. Okay. This is the economic connectedness of people by, so this is actually by county in the United States. And just to remind you, this was the upward mobility map, and this is the measure of homophily. So you'll see that there's a pretty high correlation between how connected the poor people are to the wealthy people and whether or not the poor people are later in life ending up wealthy, right? So these.
do these colors correspond to?
So the colors, sorry, so red, if you look at these, economic connectedness below 0.58 is the worst. So these mean that so if you have a 1, that means that your friendship patterns are just like they would be at random. So you have 100% of the number of friends you should have among the rich. 58% means you have only 58% of the number of rich friends that you should have if you were connecting to the rich at random and rich, to people at random. And then 1.05 is the top you get in the data, up again in the Dakotas, where the poor people have overrepresentation of wealthy people in their networks relative. So you see a pretty wide range. One thing that's interesting, and I don't have maps to show you all that, but if you look at a particular city, if you look at, for instance, the Bay Area, you'll see very different patterns within the Bay Area. So even though there's sort of broad geographic patterns, when you sort of zero in, you can see a lot of variation on the local level.
Now, if you sort of draw these pictures now, it might matter that in certain areas you have 40% of the users at Facebook, in others you have 90%. So overall, it's 85%.
Exactly. Yeah. And so we do a lot of, again, I'm not going to go into all the robustness checks we do on that, but that doesn't seem to matter here. So we don't see a systematic measurement error in that regard. Okay, so then basic question is, does economic connectedness predict household income rank in terms of, take again, these poor kids. So take a kid that grew up where their parents were at the 25th percentile, ask what their eventual income is. So how wealthy are the poor kids growing up to be? And in places with this less homophily, so higher connectedness, you see higher mobility. Places with low connectedness, high homophily, you see low mobility. Okay, so that's the basic relationship here. And then you can think of a bunch of, so here what we're looking at is economic connectedness. You could think of lots of different graph measures you might want to look at in terms of the network. So you've got the Facebook network, you say, what other kinds of things might you want to look at? Okay, well, you could look at a bunch of network measures, clustering measures, like how many completed triangles do you see in the network? You could look at spectral homophily, so second eigenvalue of the stochasticized version of the matrix. You can look at how many friendships have friends in common. You can look at other versions of connectedness, age connectedness instead of economics, language connectedness, whether people went to college, are they connected across that divide? So there's a bunch of things you can look at. And then you can look at other kinds of measures that people have used, non-network measures that people look at, like what's the volunteering rate in a given area? What's the participation in civic organizations? This is like Putnam kind of stuff from Putnam's book. So there's a whole series of the things you can look at, and so clustering, support, et cetera. So this was the economic connectedness. This was the upward mobility. For instance, here's what the clustering looks like by county. So if you look at the clustering ratio in the graph, remember clustering is when you look at when people have two friends, what's the probability that the frequency with which their friends are friends with each other? So how locally clustered is the graph? That doesn't have the same pattern as the other parts do. Okay, so there is a pattern to it, but it's a different pattern. Yeah, Alaska's, yes, exactly. Very, very highly clustered if you live in Alaska. All your neighbors know each other. Okay, so here's the correlations between upward mobility and these measures of capital. So you can begin to see these are just raw correlations. So take all these different, whatever measure you like, look at the economic connectedness, and basically this homophily measure does a much better job at predicting this economic mobility than the other measures. So that's part of the reason I was saying that this kind of homophily seems to be very important in at least one economic outcome. So this, we expected to see different patterns here. This was, I think, a little surprising to us how strong this was. You can do a multivariate regression. And actually the raw correlation is about 0.64 to 0.67, depending on county zips, et cetera. When you look at the multivariate regression, it actually pops up a little bit once you control for some of the other measures. But the other measures, in fact, some of them have negative correlations, and there's some interesting things going on. Okay, so message one just is that this economic connectedness seems to predict economic mobility. The other kind of thing is you could ask whether or not other background things about the particular community. So how unequal is the income distribution in the area? Places with big inequalities might have big immobility. So normally, the more income inequality you would have, the less mobility you would have. So if you just run a regression of upward mobility on income inequality, you get a highly significant coefficient. But once you control for economic connectedness, that pretty much disappears. So the economic connectedness seems to mediate some of these other relationships that are out there. You can do the same thing with the share. Another variable that people often use is ethnic composition of the area. So places that have high Black populations tend to have low mobility. So if you look at a raw correlation with that, there's a negative predictor. The more Black people live in an area, the lower the mobility is. But once you correct for connectedness, that pretty much disappears as well. And the same thing with, you can do a bunch of different variables. It's the same is true for upward mobility for Blacks or whites. Okay. So there's basically this pattern going on. And, for instance, it's not a racial thing. The United States is heavily racially segregated. This is when you look at only counties in the US where you have at least 90% of the population being white, you get the same relationships. So it seems that this homophily is still predictive no matter where you're looking.
Yeah, I'm a little bit sort of trying to wrap my head around this. So you're measuring the social capital right now, not the individual, but upward mobility is through the time. So how do you reconcile it?
Two things. One is what we also do, and I don't have that regression right here, but we can also look. So on Facebook, we can pair you with your parents, and we can look at your parents' income. And then what we can look at is how connected people are from their income compared to their friends' parents' income. And we can look at your high school friends. So go back, look at your high school friends' parents' income, and then see how well connected you are and see how that predicts. And so when we do that, we get pretty much the same regressions out that we're looking at here. So whether we're doing this connectedness across current income or whether we look at people's high school parents, friends' income, we get the same relationships. And so that's one of the checks that it's not just something about current income that's going on. Yeah. Yes.
You said this data now is available?
Yeah. So you can get you can download these. You can go to my website. You can download the zip file with all these measures by zip code, county, high schools, and colleges in the U.S. And all of the subset, not all those measures, but you can get about 6 or 8 of the measures.
That's not per person.
No, we didn't do it by person, and we noised up the data. So we had to add epsilon noise to the data to release it. So it has a little bit of noise in it, depending on how big the county or the school is. And we do not have individual identifiers in the data that we released. So it's all privacy protected.
I have a question, returning to my original question, when you have a split and there were these people on the boundary connected to society, then it is reflected in this data as well. Those whose parents were relatively poor, but then they become richer, have more friends from the richer community.
Yeah.
Do you see that?
So we have not tracked individual outcomes based on that. So we have thought about ways to try and do that, but we haven't looked at that specifically yet. So this is sort of the first release of the data, and we're still doing a lot of studying. And that one of the things we want to look at is more granular stuff on individual level outcomes. Okay. So different reasons. So basically in the background, there's a lot of inequality. It seems to be related to mobility as well. There's reasons we might expect that these kinds of splits in the graph would matter. And I just want to talk through a couple of them really rapidly. And then I'm just spend some time on the learning model and try and see why these kinds of splits make a difference. And I think of the sort of three different types of ways in which people, splits can matter. One is there's basic opportunities. So for instance, many people get jobs through networks. And if your friends are unemployed, it's hard to get a job and it's hard to get a job interview. So that's one thing. And I've actually done work with Nicole and other where we have papers on how networks it can lead to inequality as a result of the homophily there. So job contacts, these are opportunities. Peer influences, we talked about that yesterday. So peer effects, choices, complementarities. If everyone in my high school is dropping out and not studying, it's harder for me to study as a teenager. And so that's going to be another factor. And then there's just basic learning. Is there information getting to me about what I should be doing to get into college, or what opportunities there are in terms of fellowships or scholarships, or various things like that? Is that information getting to me, or is it stuck somewhere else in the network? So these are three basic ways in which these kinds of things can matter.
Be very careful using words like forces, explanatory factor. You never say causality. That's for the reason that you're not claiming the causality here, or it's causality is about the concept.
Yeah, so there's certain things that we can claim causality about, and a lot that we can't. So a lot of the stuff that I showed you is correlational, it's predictive. So it's observational data, and we don't have experiments. What we are doing now is we're tracking. You can track kids, for instance, of parents who move a lot. So take a kid in the armed forces, they end up growing up in different places. You can see, does that impact? So there's other ways you can actually get some random variation where you can start to get causation out. But the raw kind of data I've showed you so far doesn't have causal inference in it.
So you have some kind of a proxy of controlled experiment where you can actually.
Yeah, and there's other, there's lots of clues in the literature where people have looked at sort of, random assignment of roommates, random various kinds of things to sort of get at these things on some small levels. Getting big scale causal evidence is pretty difficult. And so, I think these are suggestive, and then the models can give us reasons why we should expect this to all hang together. And I think it's useful, these are important policy issues, and so people are doing policies anyway, and so at least this gives us some way of understanding what might be good or bad policies, at least what kinds of things matter and why there might be problems, even if we don't have causal inference yet. But it's a big issue in this literature, especially since the networks are endogenous right there. Okay, so just in terms of referrals mattering, this is an old literature going back to Myers and Schultz. George Schultz, our former Secretary of State, and Mark Granovetter, famous sociologist. So a lot of people have worked on this topic. So it matters, and there's causal inference on this. So if you get a random roommate assignment and your roommate is has better outcomes, you end up having better outcomes. So there's evidence of that. Random refugee resettlement into areas with existing populations that have better outcomes end up having better outcomes. There's studies of random assignments to military units, and then your future friends' employment predicts fairly large spillover in your probability you end up being employed. So there's a lot of evidence that this matters. The peer pressure stuff we saw yesterday, right? So if we have a network which has this kind of strong homophily, it's very easy to have equilibria. If the teens are following the majority of what their friends are doing, it's very easy to have them choose not to go to college when another group is choosing entirely to go to college. So that's another force that's happening as a function of these graphs. And then what I want to spend the rest of today on is just a simple learning model to see how these kinds of splits would affect information getting from one part of a network to another part of a network. Yes.
One quick clarification on the connection between economic connectedness and homophily. As far as I understood, the economic connectedness means you're connected with people with higher than median, but homophily would mean like you're connected to those similar to your income. And what kind of connection did you see between those two metrics? I understood the part on economic connectedness.
Yeah, so I guess a basic way of thinking about homophily would be that there's some bias towards your own populations of other people who are similar. And here what we've done is we've just done a binary cut of the population and called half of them rich and half of them poor, and just saying how well connected are the poor to the rich on average. Whereas you could imagine, you could actually, originally what we did is we did it by quintiles. You can divide them into fifths. With quintiles, it gets harder because some of the counties have no, people in the top quintile, or, so there's less coverage of sort of, so we did 50-50 because you get more, it's better. But you can do it on a very granular level. So you can ask, how connected are people with incomes between 10 and 20,000 to people with incomes between 60 and 80,000? You can see all those patterns around the country. So the beauty of having 70 million people is, you can really fill those bins, even though they're smaller bins. But we're just doing it on a binary level. Okay, so now this simple information model. And this is what I'm going to do is just do the group model, which is, I think, a really beautifully simple, nice, elegant model. So it's from Morris de Groot in the 1970s. There were earlier incarnations of it in the literature, but de Groot was sort of the first person to formalize it and prove some things about it. So similar to the Rashomini story. So individuals, and they're going to be connected by some weighted directed network. So these are going to be the people you pay attention to who influence you. And we'll call, think of this as the T stands for trust networks, but it's some stochastic matrix. So each person has a weight 1, total weight 1 going out, and it's just allocated, maybe 30% to this person, 70% to this person, et cetera. So you start with some beliefs or attitude, et cetera, some number at time 0 in 0, 1. You could make these vectors, et cetera, but I'm just going to deal with the case where these are nice real numbers, just put them in 0, 1. And then what's going to happen is over time, you're going to learn from the people around you. So your belief or your B at time T is going to be the average of what your friends had at T minus 1 weighted by this T matrix. Okay, so a really simple situation. So you can start, like an example here is there's 3 individuals. This person puts half weight on themselves, half a weight on person 1. So you can have self loops here and sort of how much you pay attention to your own information versus other people's information. And so there's a weighted directed graph, and it's going to be row stochastic since these things are always summing to 1. Okay. And then what happens is you start with some initial beliefs. So maybe this person knows about something in the graph, and now we're going to ask, what happens over time. So the other people start with belief 0, this person starts with belief 1, and now they're going to update. And so, they begin, this person's averaging a half of a 0 and a 1, this person's averaging a third on 2 zeros and a 1, and so forth. And so you just go through, and this model then has really nice, simple dynamics. Okay, so it's going to converge in this case to 2/7 on each node. So each node would have that. Okay, so one interpretation is beliefs. Another would be going back to yesterday's talk about actions. You could think of this as best responses to some action, right? So there's, we're all trying to figure out what's the norm of behavior, how much should we be doing something, and this is just, I keep trying to best respond to what my neighbors are doing, and then we're just doing that dynamic. Okay, so that's this process, and here we get a nice answer.
About the convergence issue, if you look at this, can you show that this operator T or stochastic matrix should be a little bit contracting so that it converges to something, no?
So remember it's row stochastic, and what I'm going to show you is exactly I'll give you a theorem in just a second on exactly the convergence properties. So it will converge in most cases as long as this is aperiodic. So it has a lot of nice features that go back to Markov chain theory. So you can leverage a lot of things from Markov chain theory. This is borrowed from Ben. This is a nice picture of, like, let's suppose these people start out with 1s, these people start out with 0s. This is the network. And in this case, let's just have people average equally, put equal weight. If I have 3 friends, I do a third on each. And then if you just go through time, what's happening here is, the people who are connected to others who had the belief 1 are sort of, going halfway. And there's some people still stuck at 0 and so forth. And eventually, this is going to sort of smooth out. And what's happening in this model is it's going to just keep smoothing until eventually, everybody's of the same color. Okay. And that's going to happen as long as you don't have as long as this is strongly connected, so there's a path from a directed path from each person to everybody else, and you don't have just even cycles, for instance, in the graph. You can have an aperiodicity in the graph structure.
So you could solve the latter by just everybody pointing to themselves.
Exactly. So at least as long as one person points to themselves, that's enough to kill the periodicity in the graph, and we'll actually give you convergence here. So convergence is really easy to get in this model. So you have these different interpretations. A couple of features of this, which is actually, people think of this as a bug compared to Bayesian updating. This is strange, but compared to human behavior, it seems to be more predictive. So there have been people doing field experiments comparing Bayesian learning to this de Groot learning. De Groot learning seems to do a better job, at least in some experiments, of predicting behavior. Part of the reason is for these two things. So let's imagine this person starts out with a high belief. These people start out with zeros. Okay, double counting. Well, this person is going to influence both of these. And now this person, if they were a Bayesian, they would realize, and they knew the structure of the graph, they would say, well, both of these people got influenced by this person. They wouldn't pay as much attention to that. But in this model, both of these people equally influence that. So it's sort of like, what's called correlation neglect in the behavioral literature, the psychology literature, here comes through in this, because I can have multiple paths that come through to me. So I have that kind of feature. So that's one feature of this model. Another feature of this model is echoes, right? These people are now influenced by this person, and then they're influencing back. So my belief influences other people and then comes back to me. So there's these different forces which tend to be there in at least in some parts of the literature. Okay. So let's say that T converges if the limit of T to the T times some initial belief vector exists for all beliefs. Okay, so here's an example of non-convergence, right? You just have this, people waiting. This graph is just going to blink back and forth. So you can write down examples, but they're fairly peculiar examples. They've got to have some specific periodicity structure to the cycles of the graph. Okay. So we'll say that T is aperiodic if the greatest common divisor of its directed cycle lengths is 1. And then it's easy to show if you've got a strongly connected network, meaning from any node you can follow a directed path and get to any other node, then T is convergent if and only if it's aperiodic. So aperiodicity is easy to satisfy, as Christian was just pointing out. All you need is one person who pays attention to themselves. You're going to have that work, and then you're going to get convergence. So it's a very simple model that's going to converge fairly generally.
How do you know you converge to a constant of limits?
Well, that's part of the definition. Is here you're converging. Convergence means that you have a single limit, a well-defined limit.
Because your T to the T applied to B is still a vector, right?
Yeah, it's still a vector, and basically what's going to happen is everybody, in fact, everybody's going to have the same belief, so there's going to be a consensus as well.
Can I see that easily?
Yeah, so it's not direct from this. So first of all, you're going to get to some limit. Then also T is going to be primitive. So that means that eventually so when you look at T to the T, all the entries are positive after some T, which means that indirectly I'm eventually getting information from everybody. So you've got a primitive matrix. Then you're going to reach a consensus, meaning everybody's actually believing the same thing. And this consensus is going to be determined by looking at what the initial belief was and looking at the eigenvector centrality of individuals in this network, and then hitting that eigenvector times the beliefs. Okay. And I can give you, I don't have quite time to give you a heuristic proof of exactly why you get the consensus, but I can give you I'll give you a intuition for it. And then there's another question.
Yeah, so T to the T is a matrix of stationary distributions of the market. All the rows are the same, and each row is a vector of stationary distribution.
Exactly. So you just leverage a lot of Markov chain theory in this model. It's basically almost like it's sort of like a flipped, an inverted Markov chain. So it has all the same properties, and there's a lot of the theory there. And basically what is happening is T to the T is converging to a matrix that has all the rows being the left-hand side eigenvectors here. Normally, it would be the right-hand side on a Markov chain, but it's just reversed in this case. Okay, so part of the, just the intuition for this is given a strong connection, you could sort of think about who has the smallest belief in a society. Well, whoever's got the smallest belief, either they're connected to somebody with a higher belief or they're connected to only people with a smaller belief, but eventually there's somebody with the smallest belief connected to somebody with a higher belief. And their belief is then being dragged up because they're averaging. And so, the smallest belief has to be moving up, the highest belief has to be moving down. And since this is a linear matrix, which is a constant matrix, we're not changing the matrix over time, then they're always moving by discrete amounts. So when you look at that, then the limit is going to converge nicely. Okay, so you get a consensus here. And then the thing about homophily is going to be, can we understand the speed of this convergence? How fast is this happening? And why do we care about speed? Well, a lot of information, when you think about it, how long do you talk about a particular topic? If you heard about an opportunity or something, oh, there's a scholarship available, you might tell your friends, you might tell them but after 2 weeks, you stop telling them. So if this convergence doesn't happen reasonably quickly for a lot of information, it means that information is just not going to make it. And so speed of convergence is actually important here. And homophily is going to lead to slower convergence. Okay. And so basically, if we think about a network where we have different types of people, take a stochastic block model, take a fairly segregated network, and put all the information in some group but not the others, then we'll eventually get convergence. But it could be that even after quite a few periods, there's a bunch of these individuals who are going to be relatively uninformed. Okay, so that's the reason we care about the speed. Okay. So what does the speed look like? From Markov chain theory, you can do this from Sonata. Generically, if T is strongly connected and aperiodic with second largest eigenvalue lambda2, then there exists constants such that for all beliefs, the eventual belief minus the belief at some time t is less than or equal to c times lambda2 to the t. Right? So how far away you are from where you're going to eventually be in terms of the convergent beliefs is bounded above by the lambda2 to the t. And moreover, it's also bounded below. So we can find some set of beliefs for which we're going to be at least as slow as this parameter. Okay? So that says if you've got a really high second eigenvalue, then that means you're going to converge very slowly. So there's some beliefs that you can get for which it's going to take a long time for this to converge. Okay. And again, just a quick, some of you probably know this fairly well, but let me just give you, they're not right there, but I should point there. And then, so I want to give you that would be a disaster, right? So why is it that we're getting this convergence here to lambda2? So take T and basically you can write, right? So you can write a matrix if it's diagonalizable as these are actually the left-hand side eigenvectors, right-hand side. So there's a matrix of eigenvectors, this one, and then if you want to look at what T to the T looks like, it looks like this thing to the T. So for diagonalizable matrices, this is a simple way of writing these things. So you've got zeros here, and then you've got these here, lambda to the T. It's going to look like all these things to the T. This matrix is stochastic, so the rows sum to 1. That means this thing is 1. And so what this limit eventually looks like is governed, like how close you are to the limit. Eventually, these things are the second largest eigenvalue is going to be below 1. This thing is going to converge to zeros. And so how quick you get there is how quick the second largest one is getting to 0. So if this thing is really big, then that's going to move you really slowly. Okay. So big second eigenvalue, slow convergence. Small second eigenvalue, this thing's going to look like zeros pretty quickly. You're going to get to that limit very, very quickly. Okay. So that's sort of a hand wavy proof, but you can actually make that formal, and that's the way that these things
You
improve.
want something much more local. So you have the US lambda 2 is I don't know what, but I don't care about it. I care sort of what my local lambda 2 around New York is, whatever that means.
Exactly. So actually, in the data we released the spectral homophily for each zip code, each high school, each college.
So you just look at the subgraph.
You can look at the subgraph of that area, and then look at how connected those are, and you can look at those lambdas, and then see what they look like, and then see how they govern the mobility and so forth. So that's something released. I'll tell you a puzzle and an answer to that in a moment. But yes, you want to look at that on whatever your relevant network is in order to see where things are going. Okay, so we've got this convergence being governed by this lambda 2, and then for instance in this network, lambda 2 is 0.99. So that's really, really slow convergence, right? If you put all ones up in this part of the network, it's going to take a long time for the ones to get down here. Okay, so now I'm going to tell you about a result. Yeah.
What's the lambda per community? Do you know what's the lambda 2 within the community?
Oh, within these, I don't know. No, I don't know if you start looking inside the communities, what the lambdas would look like inside those. It would be interesting. Yeah. That's a good question. I'm guessing that that's much lower, but there could be additional cuts in some of these. I know, for instance, in the Indian data, you get additional sub-jati. When you look at the jatis inside, you get these additional cuts, and so it keeps cutting. This one I don't know. Okay, so let's look at a very simple block model, and then I'm going to give you a relationship with Ben between homophily and this lambda 2. So let's just take M equal size groups, make it the simplest possible homophily model we can have. You have some probability of connecting to somebody within your same group compared to somebody who's different. And generally we'll think of the PS as being bigger than the PD. So that means you're homophilistic. How big it is compared to PD tells you how homophilistic the society is. And then let's let P be the average connectedness in the society. Okay. So, this would be drawn from a symmetric block model. There's 4 different types, and they have higher connectedness within than across. Okay, so that's a simple model. Let's make sure that P of n is bigger than log squared n over n. So it's a little bigger than the usual connectedness, but that's going to give you additional bite in looking across communities. And then let's just bound how homophilistic it can be. So we're not going to allow for we're not going to allow the network to completely bifurcate. We'll put a bound on that. And then just look at a simple case where you equally weight all your friends. So you don't have some friends that are more special than others. Okay. So from a paper with Ben, 2012, let's let a homophily measure be the difference between your same connected probability compared to your difference probability. And let's normalize that by your average probability. So let's look at how different you are compared to, what's your probability of same versus different. Theorem that then lambda 2, this homophily measure converges to lambda 2 in probability. Okay, so basically when you're looking at this lambda 2, the homophily measure in a stochastic block model is going to tell you what that lambda 2, that second largest eigenvalue is. Sorry, yes, 0, yes. No, yes, that should be a 0, yes, definitely. Okay, then you can also do consensus time. So let's look at the minimum. So look at some epsilon and look at what's the worst belief in terms of how long it takes you to get within epsilon of where you're eventually going to get. So, the beliefs you could get, you can put all kinds of different beliefs on the network. We can ask, how long does it take you to get to that eventual consensus? And so this is a measure of consensus time for some trust matrix that we've got. We can ask how long does it take to get within epsilon of the limit, okay? Then another theorem is the consensus time is within a factor of 2 with a probability going to 1 of log n over log of the homophily. I mean, minus it because this is a number smaller than 1. So the log of the homophily actually tells you something about what the consensus time looks like. And for people who, there's a lot of people here who know a lot of random graph theory. If you know about average distances in graphs, average distances usually look like log n over log of the degree. Here you're getting this consensus time, the speed of consensus looks like log n over log of the homophily, basically. So there's sort of an interesting comparison there. There's other things you can prove. So this is like a really restricted version of this. We had a sort of follow-up paper where we said much more about measures of homophily, and you can do much more general measures of homophily, but the homophily seems to look a lot like this. The second eigenvalue does pick up sort of the worst cut in these graphs really well.
Homophily measure h of n versus second eigenvalue or the kind of isoparametric type of edge expansion. Do you have a kind of relation, low bound, upper bound?
Yeah, so we have tighter bounds in the second paper where we can actually show exactly how these bound. And I don't know, I think it's actually related to modularity as well. But I don't know the precise relationships. I'd love to hear more references on the particular one you're thinking about. But yeah.
But this is something else because it says to do the second is just eigenvalue versus edge expansion ratio and homophily quantity. So it's a little bit perhaps related, but not quite. This cut, of course, has to do with edge expansion properties.
Yes, right.
But I don't see the quantitative relation.
No, it's a little different because it's really asking for ratios, not just the cuts, but the relative ratios of those compared to the links on the other parts of the graph. Right? Because the weights are determined by that.
Quantitative results.
There are Cheeger-like results on that, but there. So
with the Cheeger.
Yeah.
Yeah, these are related to Cheeger bounds. Okay, just in terms of keeping us on time then. So what do we have? Homophily is a pervasive human phenomenon. It seems to strongly predict economic outcomes and again, predicts here an equilibrium structure of games on networks, opportunities, learning, all of these things seem to be situations in which these cuts matter. And there's simple models in which you can quantify the relationship between homophily and then speed of outcomes on a graph. And so it seems to be an interesting thing for further study. And then one last comment, we actually look at spectral homophily in the Facebook data, and it turns out not to be that predictive of the income, whereas the eventual mobility. But it turns out that the economic connectedness is highly predictive. And so we wondered, what's going on there? And I think the answer to that is when you look at spectral homophily, sort of the worst cut in the graph, it doesn't necessarily fall along income lines. So most places in the US tend to have high spectral homophily. You can find some dimension on which people are split. But it's not, it could be like, Republican Democrat split, but maybe not along income split. And so when you find really split graphs, that doesn't necessarily mean that you're going to have immobility or this kind of lack of income stuff. You need that to be happening among the rich and the poor. And so it seems to be that then, this was what Christian was saying, is sort of, you want to be looking at the particular cuts that you're interested in. Those are the ones that matter. And so homophily, might not be reflected through the just the basic things in the graph. You have to look at the labeled graph to see what you want. Yeah.
I wonder if you look at the lower dimensions of the spectrum, like further down in the eigenvectors, to see whether you recover some of other partitions of interest.
Yeah, I mean, definitely when the further cuts in the graph will come out of those other eigenvectors and eigenvalues, here, given that the first one tends to be so high, it can be that some of the other ones would give us information about whether or not there's good secondary cuts or whether there's just one split in a given society. But we haven't looked in the data. I haven't seen much difference. In the theory is mostly asymptotics, and so that it doesn't pop in that quickly. But you can get more exact expressions for how these things are converging based on that whole spectrum.
It seems that in all of the models you have described, the edge weights are fixed, right?
Yeah.
Do you have any idea of like the graph where the edge weight can change?
Yeah, so there's a bunch of models that people have looked at where you adjust these things over time. For instance, one example would be that they just die out over time. Once I've talked to my neighbors 3 times, I stop, listening to their new beliefs. So you can have those things decay over time, or you can have people. So one other model is I tend to put more weight on people who have beliefs that are more close to mine. So if somebody has belief more close to mine, then I will move. And depending on what those rates look like and what assumptions you make about how that matrix moves, you can get different kinds of results in terms of whether things converge to a consensus, whether they don't, whether you can get bifurcations in the beliefs. So there's a whole series of variations on the group model that have been looked at.
So when you try to analyze network data and you have covariate data, okay, so in a social network, anything that's not the network structure, what people like, text or tweets or whatever. So something that I've seen in predictive analysis is that your prediction performance based just on the covariate data is so good that you can basically throw away the network. Is that something you see here too, that there's such a strong signal? So like with your homophily, if I had just had that other signal, that is predictive homophily.
Yeah, so I mean, I think at least in terms of the basic ones we've looked at, like in the Facebook.
You saw the exact opposite, right?
Yeah, we saw here that in fact, in this particular case, you need the labeled network. So one thing that was interesting is like when you look at these ones, you look at these other kinds of things like how unequal it is. So you hit
those are not covariates, right? Those are like exterior data, county level, if I understand correctly, or something like that. Right?
Yeah.
That is not what individual data on the network.
Right. So I guess the question of, I mean, I don't know the right way to quantify the data, in a way. So one thing we can say, just an example, 2 different high schools, one large and one small. Small high school, so small high school being less than 100 students and another one more than 1,000 students. Dramatically different homophily with the same characteristics of the students. So we actually go through different comparisons on high schools and, looking at pretty much demographically identical subsample of a high school, you'll get much more connectedness in the small school. So it seems to be something also about the institutional details or the organizational structure around people that matters. But I think we're past, we have to stop. But yeah, we can talk more about it. I think it's an interesting question. Yeah, sorry, yes. Thank you.
Thank you so much.
Yeah.
It's tea time right out there.
Is it tea time? No.
I think it's a tea.
5 minutes.
So give a quick talk.
So we have the 15 minutes.
Now we have the 15 minutes.
It's my coffee time.